like always looking for new ways to realize
Yes, I'm aware. Do not worry. I'm planning on teaching class. Just kidding. I want to see the future.
that's
That's what we're going to start.
we're presenting 16
Yes.
Okay, so we are nearing the end. There are 3 more classes. Right? So we are nearing the end. Today we'll finish our discussion on attention, and we won't go in depth. I'll just give you an idea of what is attention, not exactly how to do it. We'll have to go in depth, and it's in depth into the mathematics and all the structures. So I don't want to go there. If you're really interested and you show a lot of enthusiasm, then maybe I'll go. We have 2 more classes left. But the plan is to quickly finish off the discussion on attention and then look into final exam review. So let's look at some possible types of questions I might ask you. So that is the plan. Now, before we start, there was a question from a student who emailed me that there is a confusion between value-based learning and Q learning. So value-based learning is reinforcement learning and Q learning is Q learning. So what is the difference between value and the Q function? Now, let's reiterate. So value, we said that okay, value is a property of a policy, so is Q. So value is a property of a policy which says that okay, you start from wherever you want and you execute the policy for however long you wish to. Each policy will have a number associated with it, and this number will be related to the reward in some form. And so that number is the value of a policy. If you execute for a long time, what reward do you get? On the other hand, Q, what Q function or Q value says is that, let's say you start at a particular stage, you can start at whatever stage you want. So Q is parameterized based on what state you start at. So let's say you start at S. Q says that fix an action, take that action. So you're in state S, you take an action A. Now, the fact that you took an action, you went to a different state. From there on, how much value do you get? So Q, if we do Q learning assumes Q learning is greedy because it assumes that you will take the best step possible in the current state. And then you evaluate policies based on what further value you get. So that is why Q is greedy. Q value does not mean that it is the reward for the best possible state that you could have taken now. It's not the reward, it's not the immediate reward. Q value says that you fix an action, take the best possible action that you can take in the current state. Now, what is the result of you taking this best possible action on the entire policy? So Q value also looks forward. It also says that okay, you have to execute the policy for infinite number of times, but it fixes the current state and the current action that you take. But value, on the other hand, you can fix the current state, but you don't fix the action. So that is the difference between value and Q. And why is it easier? Q learning is basically easier Why it is easier? Because in value-based learning, you don't even know the current step or what current action you are taking. But in Q learning, you know the current action. You can take a greedy approach. So Q learning is a suboptimal solution. Even value learning, when you do and you try to figure out the optimal solution for value, you can get optimal solution if you do brute force. But the thing is, the algorithms that you have for reinforcement learning based on value, that doesn't give you optimal solution. It gives you suboptimal solution. But if you do Q learning, even if you could have solved the Q learning problem perfectly, still it will give you suboptimal solution because it's a greedy approach. Right? So that some student asked me the question. That's why.
So value-based learning is reinforcement learning. Q learning is not reinforcement learning.
Yeah, still the same MDP. It's still learning the MDP.
So is Q learning also reinforcement
Yes.
learning?
Yes. It's still reinforcement learning, but it is taking greedy approach. Now we were discussing something else. We are discussing attention, right? And we are saying that okay, we want to do a we want to model time, right? So one of the ways we said that we can model time is use some autoregressive function, some linear combination of. So IT is a linear combination of IT minus 1, IT minus 2, IT minus 3 and so on. You can do that. Now we said that okay, can we do it for a random process? We said Markov chain we have, but Markov chain doesn't really model time. Why? Because it doesn't have memory. And Markov chain models time, but it doesn't have memory. It always says that okay, whatever happens next just depends upon whatever happened now. Right? So can we extend Markov chain to consider memory? Turns out we can. We can use hidden Markov model, right? We said we showed some examples. We showed 3-level memory, right? Hot, cold weather versus whether you have a sore throat or no, and then how many ice creams you have. So this is 3 level of memory you have. Actually 2. The last is an output. So you have some memory using hidden Markov model. But the problem with that is that if you want to have n bits of information you want to store as memory, you have to have 2 to the power n hidden layers. That's exponentially large number of hidden layers. So that's why you cannot use hidden Markov models for large memory, where you need large memory values. So what cases will you need a lot of memory? We discussed this language models, right? Let's say you're translating a sentence which is 50 words long. Now, who writes a 50 words long sentence? I don't know. Whoever writes it, it's not pleasing to the eye. But still, people write it. Let's say I write a 50-word long sentence. So how do you translate that? Let's say the last word was related to the first word. So how will you keep that much memory? So 50 levels of information, then that means 2 to the power 50 hidden layers you have to have. That is huge. That's a hidden Markov model you cannot use. So what can you use? So people came up with this structure. It's called a recurrent neural network, RNN. And it's called an RNN. So what is the structure? So basically our idea is we have to figure out some way of representing this, right? IT and some weights. Let's say it's a weight vector. So we want to represent it as some function of this. And we should not just represent linear functions, we should also represent non-linear functions. So how to do that in a very generic way? So what people came up with was this structure. Maybe what you can do is, let's say you have these inputs. So this is a neural network, so that means it will have neurons, right? Neurons and layers and all that. So let's say you have these neurons and you call this input layer. This is the input layer, right? Now what are these neurons? What do they correspond to? So this is IT. This is IT minus 1. Or rather, okay. No, let's say this is IT plus 1. And this is IT plus N. And so on. You go for infinite number of times, let's say that is feasible. So this is input layer. Then you have something called a hidden layer. You have the same number of input layers as hidden layers, and you have an arrow here, right? And then finally you have the output layer. The output layer is YT. Sorry, plus YT plus N, right? And you also have arrows between the hidden layers. This structure is called a recurrent neural network. What do you get out of it? The thing is, try expressing YT plus N in terms of all this. Consider the simplest neurons. Consider that this is just an MLB, not MLB. Consider that this is just a perceptron for the time being. For the time being, consider the hidden layers are just perceptrons. Right? And consider. Okay, yeah. Consider that it's just MLBs. So if you want to represent YT plus N using this, how will you represent it? So what is this output? YT is initially W1 IT, right? Some tan hyperbolic, some activation function, right? So let's say YT equals tan hyperbolic WI IT, right? Let's assume. Then what is YT plus 1? YT plus 1 can be tan hyperbolic WI IT W hidden plus W1, let's say W1 W hidden 1 plus W2 IT plus 1 tan hyperbolic. Right? Let's rewrite because let's rewrite cleanly. YT plus as tan hyperbolic WH1 tan hyperbolic W1 IT plus W2 IT plus 1. Maybe there is may or may not have bias. Let's say may or may not have bias. Now this grows on. This grows, right, as you go further to the future. As you go further to the future, so YT plus N will be a huge nonlinear function of the history, right? And this can go forever, however many nodes you want. This can go forever means it can go for infinite number of times. Now you might say, okay, then you will have to have infinite hidden layers. Well, no. What you can do is instead of, you can represent this by a much simpler architecture. Just represent it as this. This is input IT, this is hidden layer, have an arrow, self arrow, hidden layer, this output layer, YT. Right? So this is the unrolled version of this. Right? This is the unrolled version of this. So that is recurrent neural networks. Now you can have a more complex version. So this is just one, right? Now you can have many of these and then connect them. Right? So it can get very complex. So it learns a lot. It learns a nonlinear function, and it can be infinity because now how many times you go over this arrow depends upon you. Right? It just depends upon the simulation steps you take. So it can be infinity. It doesn't increase the resources to be infinity. It's just one, just has a self arrow. Right? So that is recurrent neural networks. Now the problem with recurrent neural networks is how do you learn these weights? So let's again consider the unrolled version. So this is the unrolled version, this is the actual RNN. This is the unrolled version of RNN. So let's consider the unrolled version. We know backpropagation. We have talked about backpropagation in neural networks. So this is recurrent neural networks, means it is a neural network. Right? So you can apply backpropagation to learn the weights. You can do that. So if you apply backpropagation to learn the weights, there is a problem. The problem is, now as you are going over time, that yt plus n is your output, because that is what you are modeling with respect to it plus n, it plus n minus 1 and past, right? That is what you are modeling. So yt plus n is your output. So when you do the forward pass, you will go from it to it plus n. And when you do the backward pass, you will go from yt plus n back to it. Right? That's what you are going to do. So that is the forward pass, this is the backward pass. Yes?
In here we count the neural nodes to be the hidden layers to be only one node?
Yeah, for now. But you can have complex architectures using that. Yeah, so for now it is one. But if you unroll, there is a number of hidden layers. So I am discussing the simplest form. You can have many complex forms of RNNs. So now the thing is, okay, so if we do backpropagation, what do we do? What do we basically do? We take the error, right? So error means what? There is we do a forward pass with random weights, we get a yt plus n, but we observe a yt plus n, so there is this error e. Right? Between observed and what we actually get with the forward pass. Then how do we do the backward pass? What is the one step back? One step back is we have to differentiate the error with respect to the weight, the last layer weight, right? So that will give us the one step back error. Then how do we get two step back? We have to again differentiate the one step back error with respect to the two step back weight. Then you differentiate the two step back error with the three step back weight, and so on. Now when you do that from mathematics, I am not showing the mathematics, but we have seen the mathematics before. When you see the mathematics before, what do you do with that del E over del W? What do you do with it? You update the weights with it, right? You do W initial equals the del E del W multiplied by some change, right? And you add it. And that's how you update the weights. Now, as we have seen before during backpropagation, when we discussed backpropagation, that del E del W I, as you go back in the steps, you see that change gets multiplied. Right? So you multiply the differentials. Del E del W, one step back, multiplied by del E del W, two step back, multiplied by del E del W, three step back, and that's how you get the four step back difference, right? And that is what you add to the weight. Now if you consider that you are using a tan hyperbolic function, if you are using a tan hyperbolic function, it is always keeping your value between 0 and 1. What happens when you multiply fractions more and more, becomes smaller. So if it becomes smaller, then what happens is that as you go past, the weights don't change. The weights don't change. Right? So what happens is that the hidden layers which are more closer to your input gets higher weights. Their weight grows, and in proportion, the earlier layer weights don't grow much. So what happens is that earlier layers, they don't get much say in what is the value of yt plus n. As you go way past, they don't have much effect on yt plus n. So this is called the backpropagation through time effect and diminishing past. When you do backpropagation through time in RNNs, the past contribution diminishes progressively. That is a problem. Why it is a problem? Because now, when we talked about hidden Markov models, we couldn't model that much memory because we needed a lot of hidden layers. But now we can, but what is happening is that the past is not getting weighed in. We can model a lot of past, but it is not getting weighed in. So what is the point in modeling a lot of past? Right? So RNN doesn't work. Then what people thought about is that maybe we can forget some of the memory, and maybe we can tell that okay, some past is more important than the present. So we can maybe we can factor in, or we can give some more weights manually. We can give some more weights to past values and lesser weights not really more weights. Weights are the same. Weight learning is the same. Maybe we can factor in past values more and reduce the factor of certain present values. Right? So when we talk about LSTMs, so that is long short-term memory, right? LSTM networks. So people propose LSTMs. And there has to be a way of weighing in memory, different amounts of memory. So what they do is that they have the same architecture of RNN. Right? You have the RNN, you have the input, you have the output. Now you have two more things, the memory gate and the forget gate. Now here the input and output layers are also called input gates and output gates. Why do they call it gate? I have no idea. And this entire thing is called a memory cell. If you remove the memory gate and forget gate, then this is just an RNN. Right? Now exactly what they do, I don't want to go into it. It will take a lot of time. We have to write a lot of equations. Right? So I don't want to go into it, but what is the basic idea? The idea is through these gates you can control how much of memory do I allow and how much of it I forget. How much of input I allow and how much of the output I let go. Right? You can control this using certain control parameters. Now these are not just one arrows. So this input arrow is one, output arrow is one, but forget gate and memory gate can have multiple arrows coming in. So what you can do is you can select multiple different memory and they can come in. You can select multiple different memory to forget, and you can do that. But typically what happens is that you end up having all arrows coming in to the memory cell. And you try to train, okay, which arrows get what weight. Right? So basically from all memory cells these arrows come into memory gate and forget gate. So LSTMs are a little bit better than RNNs with respect to giving past more preference or present more preference. They are a little bit better, but it is very difficult to learn LSTMs. If you don't have a lot of data points, you don't learn much. Right? So again, it will, if you have all arrows coming into LSTM, so from all different memory cells, you have arrows coming into one memory cell, then it is computationally very expensive to learn. And what happens is that for a given time or for a given computational capability, you are suboptimal. If you had infinite computational capability, then LSTMs might have performed better. But if you have a limited computational capability, you can't do much with LSTMs. Right? Not only computation, you also have to have data, a lot of data. If you don't have a lot of data, you can't do much with LSTMs. So to alleviate these kind of problems, the concept of attention came into picture. So what is attention? It actually came from image processing domain. Right? It actually came from the image processing domain. So in image processing, you use CNNs, and you use CNNs to automatically extract features. But turns out that that is not really working in many different applications. CNNs may not work in many different applications. You might have to guide CNNs to look into certain specific features. Okay? So it's like a hybrid. At one point you are saying that okay, CNN is great because it's automatically extracting features, but at the other point you are saying that no, maybe it's not so great because there are so many features that CNN gets confused. Right? Or maybe I do not have that much computational capability to let CNN explore all features. Right? If it could explore all features, it would be better. But maybe I don't have the computational capability. So what I can do is I can guide the CNN. Say, oh, no, don't look at these, maybe look at those. Right? We can guide the CNN. So that guiding mechanism is called attention. So you can tell the deep learning system which data points should I look for. You can manually tell that okay, don't look at t minus 5. Look at t minus 6, 7, 8. Don't look at 9 and 10. Right? You can tell the RNN that. That is called attention. You're giving the RNNs some things to be attentive about. Now that concept now is extended further. Now says that okay, attention is great, but why do I have to give it manually? From the data, can I learn which part to be more attentive of? Can I learn the attention itself? Right? So that is called attention learning. And that is a much more difficult problem, attention learning. So the paper that we are talking about, which is that the DeepMind paper, the deep reinforcement learning with attention using slate MDPs, right? So the attention is that, like there, we saw that slate MDP is much more difficult than just the simple MDP. Right? So if we do attention learning, then within a shorter computational capability or within a shorter time span, what we can do is we can learn more if you give attention. Right? So that is what is attention. So we so your final exam will be up to this point. Right?
Will it be takeaway or in class only?
What?
Final exam?
In class. Yeah. We'll do what? Did I say takeaway sometime? I didn't say takeaway, right? Yeah, so in class.
Is it comprehensive, like the midterm syllabus is also included?
Yes, the midterm is comprehensive, so you have to study a lot. But mostly after the midterm. So why I say that is comprehensive? Because when we talk about things after the midterm, you will need some concept before the midterm to understand the things after the midterm. That's why I say comprehensive. But mostly the questions will be from after the midterm. So let's go to that. Let's go to some final exam review. So what did we talk about in final exam after midterm? We talked about clustering, we talked about association rule mining, and we talked about MDP stays there and all that. So I found the solution to the book questions, but it is the first edition. I won't use these questions. But the questions will be of the similar type. Okay? So you can prepare yourselves for these type of questions. The solution to the first edition is already there in their web page, in the book web page. You can go there and you can do those practice problems because the problems will be very similar. But only for those two chapters of clustering and association rule mining. Okay. That is what those are the two chapters that we talked about after midterm, right? We didn't talk about anything else apart from these things. And from the book we didn't talk about anything else. So we started with clustering after midterm, and then clustering had two parts. Then association rule mining. And then again association rule mining has the second part, and then we talked about Markov decision process, reinforcement learning. Now let me upload this paper that we just discussed. With attention. Yeah, there is an archive paper. No, why is it an archive paper? I thought it had more citations. Let me show it to you. But that one, I think it's a different link. Okay, so this paper we talked about, you are only responsible for understanding this part, up to this part. Right, so that is page 5. You are only responsible up to page 5. You should understand MDP, you should understand this concept that we discussed, attention. I'll upload some slides on RNN and attention. So as with the midterm, all these chapters that are not in the book, you will only get conceptual questions. There won't be any analytical questions. So the similar type of questions that you got in midterm. Okay? Those are pretty typically simple. You just have to understand what is going on. So I will upload some slides on RNN so that you have a reference to it. But you don't have to focus on the mathematics of it. You just have to focus on the understanding of why it is used and why it is better than HMMs and all that. So HMMs we also did, right? So I will upload some slides on HMMs. So that's it for the final. So now that's the syllabus for the final. Now let's go and look at some questions. So I have uploaded one final review, right? Let's look at that and then we will start our final review discussion. Now some other topics were suggested. Somebody suggested generative models and GANs. I am not sure whether you are interested in it. How many of you are interested in GANs? 1, 2, 3. Raise your hand so that I can see. So not many. If 6, 7 people are interested out of 190, then it's not worth it to discuss that. Just come during my office hours, we can discuss then. Right. So this is the chapter 8, that is clustering. Right? So all these topics are there. I don't have the topics for the association rule mining here. So I will put the topics for association rule mining here. And then that will be the chapters for final exam. Now let's look at some sample problems. Let's say this problem. No, not this problem. This classification. Let's say this problem. How will we do this problem? It's an association rule mining problem. So consider the sales data for hamburgers and hot dogs as shown below. Let min sub be 25%, min con be 50%. So we know the support and confidence. This part I hate, but I have to do it. Okay, so now let's see, does the rule hot dogs to hamburgers satisfy the two thresholds? What do you think? So what is this? This is saying that how many data points are there where you have hamburgers, hot dogs. Hamburgers, let's go to the book because this problem I think is not correct. Let's go to the book because this same problem is in the book also. This one. Actually, yeah. Let's go from the book because the slide might be wrong. So let's say table 6.2. So consider the market basket transactions shown in table 6.2. So this is the database that you have. You have some question? No. This is the database that you have. So they said what is the maximum number of association rules that can be extracted from this data? So the answer is already there, but don't look at it. Right? What is the maximum number of association rules that can be extracted from this data? Including rules that have zero support. So there's no support, but still you can include the rules. So how many rules do you think? How will you figure that out? We did some calculation a long time back. We said that okay, if D is the total number of items, then how many rules can we do? 3 to the power D minus 2 to the power D minus 1 plus 1. Right. Now that this is the beauty with exam that you don't need to understand how you arrive to the number. Okay. Just use the number and write it. And this is also the beauty of cheat sheets because you can just write the equation, look at it and write the number. Right? So that's what they have also done. They have just they don't even say how they got it. They just say 602. Right? So how you got it is you have to go to this slide. And that's right. This is the way you got it. 3 to the power D minus 2 to the power D plus 1 plus 1. And how you got it is by summing those combinations. So you use that, and here D is how many? D is how many? D have you had to calculate? Oh, it is already there. It's the same calculation. So D is 1, 2, 3, 4, 5, 6. Okay, 6. And so that's how you calculate it. Then they are saying, okay, what is the maximum size of frequent item sets that can be extracted? So min sub, they are saying min sub is 0. So they are asking, okay, what is the maximum size of frequent item sets? What will be the maximum size of frequent item sets that can be extracted from that database? So now you just look at the database. You don't look at that there are 602 rules. So minimum support is greater than 0. So what is the? It has to be greater than 0. It cannot be equal to 0. Right? You cannot have min sub equal to 0. So you have to have greater than 0. So what is the maximum size of frequent item sets that can be extracted? the largest, right? I mean, they are not saying that it has to be frequent. It says that, okay, it can be an item set, but what is the maximum size? It may or may not be frequent. So that is 4. Why? Because you only have, you have 4 items, or you have an item with 4, no, you have an item set with 4 items. That's why. Then it says, okay, write an expression for the maximum number of size 3 item sets that can be obtained. It's very easy, these questions. Size 3 item set is, you have 6 item sets. How many ways can you make 3 item sets? 6C3. Right? So these are very basic questions. Then it says, okay, find an item set of items 2 or larger that has the largest support. And so you just count the support. How many times 2 or larger items are there, and just make sort it and take the largest value. Right? So they say that the 2 or larger bread and butter. Then find a pair of items A and B such that A implies B, that rule, and B implies A, that rule, have the same confidence. Now this is, so they said pair of items. So that means you only have to, so how will you go about doing this? It has the same confidence. It has to have the same confidence. How will you go about doing that? Can you first look for support and then look for confidence? Is it a good approach to first look for or rather, if 2 rules have the rules A implies B and B implies A, if these 2 rules have the same confidence, does that mean that they will have the same support? Will they have the same support? Why? Why will they have the same support? The answer is very easy. Because it's just the rules are formed from the same item sets. The rules are formed from the same item sets, so they will have the same support, no matter what confidence they have.
Can we also find the 2 items that have never been purchased together? So the confidence is always 0.
Yeah, that also you can do. That's a trivial solution, right? Find 2 items that have never been purchased. So that's confidence is 0. But then the support is also 0. Right? But that's fine. It doesn't ask us to find the support with 0. So these are all very simple questions. You'll have some of these in the example. Okay, this is one, question number 7 is good. So they are saying consider the following set of frequent 3 item sets. So you're given these are the frequent 3 item sets. And there are only 5 items in the data set. 1, 2, 3, 4, 5. Right? List all 4 item sets candidates obtained by a candidate generation process using Fk-1 F1 merging strategy. So remember Fk-1 F1 merging strategy. So you go to the K-1 kth level. You are generating the kth level. So you go from the K-1 and then look back at the first level, add 1 item set to every K-1 layers. Right? So basically 1, 2, 3, then you add 1, 2, 3, 4, so 1, 2, 3, 5, so on. Right? So these are the ones. 1, 2, 3, 4, 1, 2, 3, 5, 1, 2, 3, 6, then 1, 2, 4, 5, this, and so on. Right? So you follow that algorithm, but in the slide. So you have to remember how you, what is this algorithm. You follow that algorithm and you write the steps and what are the different candidates that are generated. And then there is a different algorithm. list all candidates, all candidate 4 items sets obtained by candidate generation procedure in a priori. So remember we used that a priori algorithm, right? What was that a priori algorithm? We did a pruning, right? We said that okay, it can be applied in many different ways, but one way is that okay, if one particular rule does not have enough confidence, no. If one particular rule does not have if one particular item set does not have enough support, then its supersets will not have support. Right? So using those a priori rules, you can figure it out. So exactly how you do it, it's again very easy. So I'm not going there. So some this type of questions you'll get. Okay, from the association rule mining chapter. And these are, if you understand or in your cheat sheet, if you write all these algorithms and all that, this is piece of cake. The other type of question is from clustering. Right? Today we will do a very brief discussion of final exam review, and then once you have gotten a chance to go through all this, then you can come up with more questions and we will discuss them. So this is one example of clustering. So they are saying, okay, use the similarity matrix in the following table to perform single and complete link hierarchical clustering. So do you remember single and complete link hierarchical clustering? What? Yeah, mean distance and max distance using, you have to cluster. Now remember, this is similarity matrix, so it is reversed. The single link is the max similarity, and complete link is minimum similarity, right? So when you say single link, you don't look for the minimum number, look for the maximum number, right? Because it's a similarity matrix. So look for the maximum number and merge those, and then recalculate. Right? So again, that is very simple. The solution is also already there in the slides. It's already there in the slides. So I am not going through the solutions today. I am just giving you an overview of what type of questions to expect. If you want me to take one question and solve it with pen and paper step by step, we will do that next class, not today. So this is one type of questions you will get. Oh, and I might ask you to draw the dendrogram. Then remember calculating the entropy and purity of the confusion matrix when you, no, this is, yeah, entropy and purity of the clusters. So that is also just formula, right? You just look at the formula and just compute, just plug in values and compute. So these are very simple things. Let me see what other type of questions. So these questions are from the base net and all that we won't ask because we already covered that in the first part. This one I don't know, I think some mistake in the problem description. I can update it. No, these are all before midterm, right? Now this one. This one is nice. So you are given the following cluster assignment and the pairwise similarity matrix. Find the correlation coefficient between similarity matrix and the ideal similarity matrix. So remember we were trying to evaluate the cluster. Right? How good is a cluster? We are talking about that. So when we are talking about that, how good is a cluster, we say that okay, the ideal similarity matrix is what? All diagonal terms is 1 and all non-diagonal terms are 0. Now how do we get diagonal terms? We have to be careful of what is cluster. Right? We cannot just list okay P1, P2, P3, P4. We have to cluster them. So here P1 and P2 are clustered, P3 and P4 are clustered. So you have to club them. P1, P2, one set, P3, P4, one another set. Right? So the identity matrix will be a 2 plus 2, 1, 1, 0, 0. No, not 1, 1, 1. No, it will be like this. So if you have P1, P2, P3, P4, P1, P2, P3, P4, then P1, P11, P1, P21, 0, 0. Then P2, P11, P2, P21, 0, 0. Then this 0, 0, 1, 1, 0, 0, 1, 1. This will be your ideal similarity matrix. Right? And then you calculate the correlation between this and the matrix that is given. So again, that is this is a little bit trickier than the other ones that we have seen, but still very simple. Well, yeah, that's what we did also.
Professor,
Yes.
I remember when we discussed about the similarity metric, we have a theorem or something. We say if the similarity should be between 0 and 1. If the similarity is 1, it means the 2 points are the same point.
Yeah, same cluster, yes.
So okay.
Yeah, same cluster. Right? It was given that P1 and P2 is the same cluster, plus cluster number 1. So for now, I don't have any other questions. What I'll suggest is go to that solution book of the first edition of the book and look at the problems. The problems will be of similar type. Now the problem is with the other half. Now I am trying to make it a problem for you because if I have questions that are either from a book or simple to answer, we faced a lot of problems in midterm. Right? So I don't want the same problems in midterm that to occur in final. So this time the next part and the reinforcement learning and all that, I will just think of some questions on the day of the final. Right? Whatever comes to my mind, I will ask. And if whatever you wrote makes sense, you'll get points. And if you write which does not make sense, you won't get points. Right? Because I cannot use book questions anymore. And those questions are baked questions, you know. In midterm, that's what that's why we are successful in doing that bake. So if I just come up with one question and give it to you, you cannot have two people cannot have the same answers. Right? If you have the same answers, you cannot say that we had the same cheat sheet because that question is not in the cheat sheet. Right? You cannot have that question in the cheat sheet. So that's how we got a lot of people. And there is going to be consequences for them. So don't do it in any other class. And I think 90 to 95% of you didn't do it. But those 5% who do it hurts a lot. They hurt the 95%. So that's why I am telling to those 5% don't do it, and telling to the 95% don't help them. Right? Don't help them do it. So this is very serious because we are still regrading midterm. You understand the problem, right? We are still regrading midterm. Midterm ended what, 1 month back, 1.5 months back, but we can't figure out like who is the original, who is the problem. We can't figure out. So we are still regrading. So it takes a long time to make things right if you are wrong. Right? So don't be wrong. So let's finish. Let's stop here today, and then we'll meet next time. Next time, come prepared with any kind of question that you want answers to for final exam, and we'll try to answer them. Oh, and wait. The TA discussed Keras, right? But do you want TensorFlow to be discussed? So you want TensorFlow. So one class I'll do the TA will come and discuss TensorFlow, and we won't talk about the generative models because there's not much interest. So if you want to understand generative models, just come during office hours and we can discuss it. Oh, assignment 4. I will upload assignment 4 today, but you don't need uploading. You just run the same thing by taking 20% of the 80% of the users as training and the next 20% as testing. That is what I will write in the assignment also. So I will post it today. Yes, everything. Just change the content. Simple assignment.
The contents. We excluded you from the report. We excluded you from the report.
That's fine.
He decided not to be part of Sixth Sense.
Protection is my bullshit.
Let's see.
But I cannot sign it unless you finish it. That's the problem. So the day you finish it, April 30, come to me, I'll sign it. Oh, so you no need to come, you just email me. I'll send an email. Just on April 30, not before that. We'll do carving. When is the final? So you look at the ASU schedule, I think it's May 2nd or so. 2nd May, yeah. So yeah, I'll follow the ASU schedule. Okay, thank you.
就是跟石头一样，会跟
First part that we talked about.
First questions, third part.
Yes.
That was 0.0.